Hello, everyone. My name is Anna Marie Vagnozzi, and I'm a lecturer at Clemson University in the School of Mathematical and Statistical Sciences. Today, I'll be sharing about a study that aims to shed light on statistical techniques for detecting partisan gerrymandering. When it comes to using mathematics as a tool to work towards fair redistricting, there are two approaches one can take. One could focus on identifying techniques to assess the fairness of maps that are already established, or one can focus on procedures to construct fair districtings in the first place. This study focuses on evaluating existing maps, but has implications for the ways that we can go about constructing future maps. The motivation for this study is the analysis that was conducted for the 2011 Pennsylvania Congressional map, which was used as evidence in a PA Supreme Court case to overturn the 2011 map as an unconstitutional partisan gerrymander. The result of this case was the plan being replaced by a less biased map in 2018 in time for the general election. Now, in our study, we wanted to do two things. We wanted to use the Pennsylvania election maps to identify measures that are consistent, reliable indicators of partisan bias under outlier analysis, and apply a similar analysis to that done in Pennsylvania to evaluate the likelihood that the South Carolina election maps were intentionally gerrymandered. We wanted to evaluate three election maps that were established following the 2010 census: the South Carolina Congressional map, which has 7 districts, and both of the state legislative maps. We also used the 2011 and 2018 Pennsylvania maps as standards for what we expect to see for a biased map and a fair map, respectively. We first needed a way to measure the partisan bias of a map. One established way of doing so is using the median mean measure, which has a long record of usage and is generally acceptable as a reliable measure of partisan bias. It's found by subtracting the average district vote share from the median district vote share, and it characterizes fairness by looking at the skewness of the vote distribution. Negative values indicate an advantage for Republicans. We can see that the 2011 Pennsylvania gerrymander indicated the most bias, while the South Carolina congressional map had a similar level of bias to that of the Pennsylvania map. And the South Carolina legislative districts fall somewhere in between. We decided to use this as a standard for measuring partisan bias since median mean was considered a reliable enough standard in the Pennsylvania Supreme Court case. But we wanted to identify additional measures of partisan bias to test alongside median mean. And to do so, we needed to establish a standard for what we mean when we say a map is biased with respect to partisanship. We used an established definition of partisan symmetry, which in essence says that if on average, party A earns a certain proportion of seats with an average district vote of V, then we should also expect for party B to earn the same proportion of seats if the political landscape were to change and party B then had the same average district vote share. This definition allows us to identify measures of partisan bias, as any measure that indicates bias should correspond to a symmetry in the relationship between votes and seats. Katz, King, and Rosenblatt showed that median mean actually satisfies this standard, with non-zero values corresponding to asymmetry in the seats-votes relationship. We identified 3 additional measures then of partisan bias for our study to compare with the performance of median mean. One of these is the bias point estimate, which measures the distance of each party from symmetry and is found using the estimated proportion of seats that we expect a party to win based on the observed statewide average district vote. It can be interpreted as the additional proportion of total seats that would have been won by the reference party under a symmetric system. Negative values correspond to a Republican advantage, indicating that Democrats would have won a larger proportion of seats than they did if the system was symmetric. We can then see that the 2011 Pennsylvania gerrymander indicated more bias than any other map, and the South Carolina congressional map again has a value similar to that of the fair Pennsylvania map. And here, the South Carolina legislative maps exhibit even less deviation from partisan symmetry. We also looked at a measure referred to as geometric partisan bias, which takes a function describing the relationship between seats and votes using observed election data, inverts that curve around the midpoint of the graphical space, and finds the area between the original curve and the inverted curve. The direction of advantage can then be identified by looking at whether the estimated seat proportion at V equals 0.5 falls above or below this midpoint. If it falls below, then it means that the reference party needs to get more than half of the statewide vote in order to win half of the seats. It's important to note here that there are two assumptions we can make when we estimate the seats votes curve. So when the average district vote for a map changes, we can assume either that the individual district vote shares shift by the same amount statewide, we call this uniform partisan swing, or that this shift is variable for each district, and we call that variable partisan swing. Now, we calculated geometric bias for both of these assumptions, giving us our third and fourth measures of partisan bias. In each of the maps that we analyzed, we see a Republican advantage regardless of which seats votes curve is used. But we consistently see that the 2011 Pennsylvania gerrymander indicates the most bias out of all of the maps. And this can be observed graphically as well. So we can see that the 2011 Pennsylvania map has a larger area between the curve and the inverted curve than its fair 2018 counterpart. And when we look at South Carolina, we see that the area between the curves more closely resembles the geometric bias that the 2018 Pennsylvania map exhibited. But looking at the bias measure of a map alone isn't enough, because even if we have a map that indicates some level of deviation from partisan symmetry, what we really want to know is how much bias is too much. Some maps are going to exhibit inherent bias due to voting geography, and just because a map has some bias doesn't necessarily mean it was intentionally drawn that way. So what we want to do is compare our map to other maps that could have been drawn under the same redistricting guidelines and see how their bias measures compare. We can generate a large sample of such maps using a Markov chain random process. We represent our map as a precinct adjacency list, and we use precincts because they're the smallest geographic unit for which voting data are available. Then each step of our Markov chain represents randomly swapping a precinct from one district to a neighboring district, thereby changing the district boundaries in the map. At each step, we then compute the partisan bias measure for that map, and then we compare the original map to the generated sample. We then apply a theorem developed by Chikina, Fries, and Pegden and used in their analysis of the 2011 Pennsylvania map to find the likelihood that a map is an outlier with respect to some label function. And here we choose as label functions the measures of partisan bias that we identified. In summary, this theorem says that if our election map is a typical districting, the true probability that we observe a map at least as biased as ours among the set of all possible districtings is bounded by the square root of 2 epsilon, where epsilon is the observed proportion of sample maps that are at least as biased as ours. What we did is we compared a variety of map constraints that correspond to various redistricting guidelines regarding compactness, population sizes, and communities of interest. Then for each run of the Markov chain, we applied the root epsilon test to determine whether our map is a typical districting. Here's what we saw. First, let's compare the biased 2011 Pennsylvania map with the fair 2018 Pennsylvania map. We compared 2 alternative compactness constraints, and we looked at what happened if we froze the minority-majority district, what happens if we compare 2 different maximum allowable population differences between districts, and what happens if we respect county boundaries. These combination constraints are listed on the left of the table. And for each constraint combination, we conducted our test under each of the 4 partisan bias measures and on each map. And we generated between 250 billion and 1 trillion sample maps. So what we see is that the gerrymandered 2011 map achieves significant results under our standard metric of median mean, while the 2018 map does not. We can then expect reliable measures of partisan bias to perform similarly to median mean, which is an accepted standard and was used to overturn the 2011 map. What we see is that the geometric partisan bias measure under variable partisan swing, which is indicated in the last two columns, performs similarly to median mean, indicating significant results on the 2011 map, but far less often exhibiting those significant results for the 2018 map. Now, on our other two partisan bias measures, we don't achieve significance, even on the known 2011 gerrymander. So they're not as useful indicators of partisan bias under outlier analysis. So then, what do we see in South Carolina? Well, the answer is not anything super interesting. Under all of our bias measures, we have a few map constraint combinations under which outlier analysis identifies a statistically significant result. Even under the median mean metric and the variable geometric bias measure, which we identified on the previous slide as being reliable and consistent indicators of bias. So we see this in both the South Carolina congressional maps and the two legislative maps. So what can we conclude from all this? Well, from our look at the Pennsylvania maps, we can say that median mean and variable geometric partisan bias both perform as consistent indicators of partisan bias, which while the point estimate and the uniform geometric bias, these are not as sensitive to gerrymandering. In addition, by applying these measures to the South Carolina congressional and legislative maps, we see that the South Carolina election maps do not exhibit overwhelming evidence of carefully constructed partisan bias. This result is valuable because if we can identify consistent, reliable indicators of partisan bias, these measures can then be considered as quantities to optimize when constructing fair redistricting plans. So thank you so much for your time, and I will be glad to answer any questions in the Q&A segment.